Imagine you have a complex raster image, a photograph of a cat sitting in front of a dog with a vase of flowers in the foreground. If you want to turn this into a vector graphic, most current tools do what's called modal vectorization. They only trace what they can actually see. If the cat is blocking part of the dog, the software just creates a fragmented dog-shaped hole. You end up with a bunch of disconnected vector shards rather than actual objects. This makes it nearly impossible to move the cat and actually see the rest of the dog behind it. That is the problem a new framework called AmodalSVG is solving. Instead of just tracing pixels, AmodalSVG performs Amodal Image Vectorization. Its goal is to reconstruct the complete geometry and appearance of objects, including the parts that are hidden by occlusions. This allows you to treat a vector image like a set of real-world layers, where you can reposition, recolor, or even remove an object while the background remains perfectly intact. The researchers achieve this through a two-stage pipeline. First, they perform semantic decoupling and completion in the raster domain, and then they move into the vector domain for the actual drawing. The first stage is called Semantic Layer Peeling, or SLP. Think of this like peeling an onion. The system needs to figure out the occlusion hierarchy, basically, who is in front of whom. To do this, they use a vision language model, specifically Qwen2-VL, guided by a chain-of-thought prompt. The VLM analyzes the scene and identifies the object closest to the viewer. Once the VLM identifies the foreground object, the system uses GroundedSAM to create a precise pixel-level mask. But here is the clever part. To make the layer Amodal, the system doesn't just cut the object out. It uses a hybrid inpainting pipeline, combining LaMa and FLUX. LaMa handles the broad structural geometry of the background, and FLUX fills in the high-fidelity textures. This effectively heals the hole left behind by the object, creating a complete background image. This process repeats, peeling and inpainting, until every object is separated into its own structurally complete raster layer. Now that we have these independent, complete raster layers, we need to turn them into SVGs. This is where adaptive layered vectorization, or ALV, comes in. Vectorizing a complex image is a non-convex optimization problem, meaning if you start with random shapes, you'll likely never reach the target image. To solve this, ALV uses content-adaptive initialization. It samples the initial positions and colors of the SVG primitives directly from the raster pixels of that specific layer, which drastically narrows the search space. But how do you decide how many vector primitives you actually need? Too few and the image is blurry, too many and the file becomes a bloated mess. ALV solves this with a feedback-driven mechanism. First, it uses occlusion-aware primitive pruning. Most tools prune based on area or opacity, but that often deletes critical fine details or ruins soft shadows. Instead, AmodalSVG calculates a visual contribution score. It looks at the rendering hierarchy to see how much of a primitive is actually visible after all the layers on top of it are rendered. If a primitive is almost entirely covered by another, it's pruned regardless of its size. Second, it uses importance-driven primitive addition. The system analyzes a residual error field, essentially a map of where the vector version doesn't match the raster version. It then uses a temperature-scaled softmax function to sample new primitives. A low temperature focuses strictly on high-error areas like sharp edges, while a higher temperature allows for more exploration of broader regions. Finally, it manages the primitive budget, using a linear extrapolation of historical efficiency. It tracks how much the loss decreased during the last few editions to predict exactly how many more primitives are needed to hit a target fidelity. This prevents overparameterization while ensuring the final result is crisp. The results are significant. In quantitative tests, AmodalSVG outperforms state-of-the-art methods across MSC, PSNR, and LPIPS metrics. But the real win is in the editability. Because the layers are semantically decoupled and amodally complete, you can take an object, like a person in a photo, and move them to a different part of the image. Because the system inpainted the background during the peeling phase, there are no holes left behind. You can resize, reorder, or even replace objects entirely, while maintaining global visual consistency. Of course, there are limitations. The system struggles with transparent objects like glassware, because the peeling logic assumes opaque boundaries. It also struggles with cyclic occlusions, like a bird's claw gripping a branch while its body is behind the branch, because the standard SVG format relies on a strict global Z-order. Despite these hurdles, AmodalSVG represents a major shift in how we think about image vectorization. By combining the semantic reasoning of VLMs with the precision of differentiable rendering, it transforms a flat raster image into a fully editable layered vector scene.